Good day. So, before we begin, let us ask the following question first. You may write it in the chat box or feel free to voice it out. In one word, what is radiation? Are you familiar with spectroscopy? How about some idea about electromagnetic spectrum? Do you remember the structure of atom? Do you have any idea about spectral lines? How about Doppler effect? In the behavior of light, you are expected to learn the following.
Good day, everyone. Today, our topic is all about radiation and spectra. As what you can see on the screen, it is a photograph of the sun that was taken at different several wavelengths of ultraviolet, which our naked eyes couldn't see, and then color coded so it reveals the activity in our sun's atmosphere. And talking about the stars we all know is so far to us, and then the nearest star is so far away that the fastest spacecraft humans have built would take almost 100 years in order to get there. So imagine, our lifetime wouldn't be enough to go there. Our lifetime wouldn't be enough in order to travel and to do so. In astronomy, most of the objects that we study are completely beyond our reach. The temperature, for example, the temperature of the sun is so high that a spacecraft would be fried long before it reached it. And the stars are much too far away to visit in our lifetimes with the technology that was available in the current time. Even light, which travels at a speed of about 300,000 kilometers per second, takes more than 4 years to reach us from the nearest star. And if we want to learn about the sun and the stars, we must rely on techniques that allow us to analyze them from a distance. So we come now to the behavior of light. Coded into the light and other kinds of radiation that reach us from objects in the universe is a wide range of information about what those objects are and how they actually work. If we can possibly decipher this information and code rightly, then it isn't needed for us to leave the immediate environment of the Earth. And understanding it rightly means we can learn an enormous amount about that cosmos. The visible light and other radiation we receive from the stars and planets is generated by processes at the atomic level by changes in the way the parts of an atom interact and move. Thus, to appreciate how light is generated, we must explore first how atoms work. There is also a bit irony that in order for us to understand some of the largest structures in the universe, we must become acquainted with some of the smallest too. Also, notice that we have twice used the phrase light and radiation, but in this chapter, we will understand that visible light is not unique, but it is merely the most familiar example of a much larger family of radiation that can carry information to us. The word radiation will be frequently used in this study and our common language. Radiation is often referred to as or described to us as a certain kinds of energetic subatomic particles released by radioactive materials in our environment. For example, the radiation we use in treating cancer. But in astronomy text, radiation is a general term for waves including light waves that radiates outward from a source. As we saw in Orbits and Galaxy in Newton's theory of gravity, accounts for the motion of planets as well as objects in Earth, application in this theory to a variety of problems dominated the work of scientists for nearly 2 centuries. And in the 19th century, many physicists turned to study electricity and magnetism, which are intimately connected with the production of light. And the scientists who play a role in this field comparable to the Newton's role in the study of gravity was the physicist Maxwell, James Clerk Maxwell, which is born and educated in Scotland. He is inspired by a number of ingenious experiments that show an intimate relationship between electricity and magnetism. Maxwell developed a theory that describes both electricity and magnetism with only a small number of elegant equations. It is this theory that gives us important insights into the nature and behavior. Maxwell theory of electromagnetism. We will look at the structure of atom in some detailed manner later, but first we must begin noting that a typical atom consists of several types of particles, a number of which have not only mass but an additional property called electric charge. And in the nucleus of every atom are photons which are positively charged, and outside the nucleus is the electron which is negatively charged. Maxwell theory deals with these electric charges and their effects, especially when they are moving. In the vicinity of an electron charge, another charge feels a force of attraction or repulsion. Opposite charges attract like charges repel. When charges are not in motion, we observe only this electric attraction or repulsion. If charges are not in motion, however, as they are inside every atom and in wire carrying a current, then we measure another force called magnetism. Magnetism was been known for so much recorded in the history until in 19th century its cause was finally discovered. Experiment with electric charges demonstrated that magnetism was the result of moving charged particles. Sometimes in motion is clear, as in the coils of heavy wire that make an industrial electromagnet. Other time, it is more subtle, as in the kind of magnet you buy in a hardware store, in which many of the electrons inside the atoms are spinning in roughly the same direction. It is the alignment of their motion that causes the material to become magnetic. Physicists use the word field to describe the action of forces that one object exerts on the other objects. For example, sun produces gravitational fields that controls Earth's orbit, and then stationary electric charge produces electric fields, and moving electric charges also produces magnetic fields. Actually, the relationship between electric and magnetic phenomenon is even more profound. Experiments had shown that changing magnetic fields could produce electric currents, and changing electric currents could in turn produce changing magnetic fields. So once begun, or actually it is obvious that electric and magnetic field could continuously trigger each other. Maxwell analyzed what would happen if electric charges were oscillating, or if the electric charges are actually moving back and forth, and found that the resulting pattern of electric and magnetic field would spread out and travel rapidly through the space. The disturbance moves outward and creates a pattern that we call a wave in the water. And for example, in this photo, the moment that the frog would jump in the water, it would create a pattern of waves, and then it would spread out in the given space. It would continue spread out in the given space. Maxwell was able to calculate the speed at which an electromagnetic disturbance moves through space. He found that it is equal to the speed of light, which had been measured experimentally On that basis, he speculated that the light was one form of a family of possible electromagnetic disturbances called electromagnetic radiation. Again, it is a conclusion that is confirmed in a laboratory experiment. For example, when light enters the eye, its changing electric and magnetic fields stimulate nerve endings, which then transmit the information contained in these changing fields to the brain. And the science of astronomy is primarily about analyzing radiation from distant objects to understand what they are and how they work. So let's come now to the wave-like characteristics of light. The changing electric and magnetic fields in light are similar to the waves that can be set up in a quiet pool of water. In both cases, the disturbance travels rapidly outward from the point of origin and can use its energy to disturb other things farther away. So, i-recall ang example to ganina, which is the frog in the water. As I've mentioned earlier, the moment that the frog jumps into the water, it will create a pattern of waves, and those pattern of waves will be the energy to disturb other organisms in the same pool. For example, a dragonfly peacefully resting in the leaf in the same pool will be disturbed by the waves created by the action of the frog. And then the point of origin would be where the frog jumped, and the disturbed things is the dragonfly. And then, in the case of electromagnetic waves, the radiation generated by a transmitting antenna full of charged particles and moving electrons at your local radio station can sometime later disturb a group of electrons in your car radio antenna and bring you the news and weather while you are driving to your class or to your work in the morning. The waves generated by charged particles from water waves is profound waste. How water requires water to travel in, while sound waves require air to travel also. But electromagnetic waves do not require water or air. The fields generate each other and can move through a vacuum such as outer space. And this is such a disturbing idea in the 19th century that scientists actually made up a substance to fill all of space, one for which there was not single shred evidence, just so light waves could have something to travel through, and they call it ether. And for today, we know that there is no ether and that electromagnetic waves have no travel at all moving through empty space. The other difference is that all electromagnetic waves moves at the same speed in an empty space, which turns out to be the fastest possible speed in the universe. No matter where electromagnetic waves are generated from, and no matter what other properties they have, when they are moving, they move at the speed of light. Yet, from everyday experience that are different kinds of light. For example, we perceive that light waves differ from one another in property we call color. Yet, the nice thing about wave is it is a repeating phenomena, no matter if it moves up or down or in a cynical way. Thus, any wave can be characterized by a series of crests and troughs. Moving from one crest through a trough to the next crest completes one cycle. The horizontal length covered by one cycle is called wavelength. We can see it in the analogy of the ocean. The wavelength is the distance that separates successive wave crests. So, for visible light, our eyes perceive different wavelengths as different colors. Red, for example, is the longest visible wavelength, and violet is the shortest. The main colors of visible light from longest to shortest wavelengths can be remembered using the mnemonic RGB for red, orange, yellow, green, blue, indigo, and violet. Other invisible forms of electromagnetic radiation of different wavelengths, as we will see in the next section. We can also characterize different waves by their frequency, the number of wave cycles that pass by per second. If you count 10 cranes moving by each other, for example, then the frequency would be 10 cycles per second. And in honor of Henry Church, the physicist who inspired by Maxwell works, discovered radio waves, a CPS is also called a hertz. Then take a look at your radio, for example, and you will actually see that the channel is assigned to each radio station is characterized by its frequency, usually in units of kilohertz, thousand of hertz, or megahertz or million of hertz. Wavelengths and frequency are related because all electromagnetic waves travel at the same speed. To see how this works, imagine there is a parade in which everyone is forced to travel in the same speed, at exactly at the same speed, and then you are standing in the corner and watch the waves of marchers come by. First, you see row after row of miniature ponies because they are not very large and therefore have a shorter wavelength. A good number of ponies can move past you each minute. We can say that they have a high frequency. Next, however, come a several row of circus elephants. The elephants are large and marching at the same speed as the ponies, so far fewer of them can march past you per minute. Because they have a wider spacing, they have a represent a lower frequency. The formula for this relationship is presented on the screen. Now let's proceed to the given example. So a car on the highway traveling at speed of 100 km per hour covers 100 km during the time of 1 hour. For an electromagnetic wave to travel the distance of one of its wavelength at the speed of time, we have speed of light is equals to wavelength divided by the time. The frequency of a wave is the number of cycles per second. If a wave has a frequency of 1,000,000 cycles per second, then the time for each cycle to go by is millionth of a second. So in general, time is equals to 1 divided by the frequency. And then substituting into our wave equation, we get speed of light is equals to wavelength times frequency. Now let's use this to calculate an example. What is the wavelength of visible light that has a frequency of 5.66 times 10 raised to 13 hertz? So in doing so, we find the equation for wavelength, which is wavelength is equals to speed of light divided by the frequency, and then substituting their values and come up with the result 5.30 times 10 raised to negative 7 meter. So we come now to light as a photon. The electromagnetic wave model of light, as formulated by Maxwell, was one of the great triumphs of 19th century science. In 1887, when Henry Hertz actually made invisible electromagnetic waves, what today are called radio waves, on one side of a room and it detected them on the other side, it ushered in a new era that lead to the modern age of telecommunications. So this brings life to our technologies today, such as our telephones, our phones, or wireless networks around the globe. Then, however, by the beginning of 20th century, more sophisticated experiments had revealed that the light behaves in certain ways that cannot be explained by the wave model. Reluctantly, physicists had to accept that sometimes light behaves more like a particle, or at least a self-contained packet of energy, than a wave. We call such a packet of electromagnetic energy as a photon. And then the fact that light behaves like a wave in a certain experiments and like a particle in others is a very surprising and unlikely idea. After all, our common sense says that waves and particle are opposite concepts. On one hand, a wave is a repeating disturbance that by its very nature is not only in one place but spreads out, as what I've mentioned earlier. A particle, on the other hand, is sometimes that can be in only one place at any given time. As strange as it sounds, though, countless of experiments now confirm that electromagnetic radiation can sometimes behave like a wave and other times like a particle. Then, again, perhaps we shouldn't be surprised that something that always travels at the speed of the universe and doesn't need a medium to travel through might not obey our everyday common sense ideas. The confusion that this wave particle duality of light caused in physics was eventually resolved by the introduction of a more complicated theory of waves and particles now called quantum mechanics. And quantum mechanics is an interesting modern science, but mostly beyond it is beyond the scope of the book. And in any case, we should be prepared now when scientists sometimes discuss electromagnetic radiation as if it is consisted of waves and other times referred to as a stream of photons. Then a photon is being a pack of energy carries a specific amount of energy. We can use this idea of energy to connect a photon and a wave models. How much energy a photon has depends on its frequency. When you think about it is a wave. A low energy radio wave has a low frequency as a wave, while high energy X-ray at your dentist office has a high frequency wave. And among the colors of visible light, violet light photons have the highest energy and red light photons have the lowest. And the question is, in the above example, again, the question is which photon would have the longer wavelength as a wave, the radio wave or the X-ray? And if your answer is radio wave, then you are correct. Because radio waves has a lower frequency, so the waves cycle are longer. As a start to propagation of light, the question is how light from a light bulb moves through space. As waves expand, they travel away from the bulb, not just toward your eyes, but in all directions. They must therefore cover an ever-widening space, yet the total amount of light available can change once the light has left the bulb. This means that as the same expanding shell of light covers a larger and larger area, there must be less and less of it in any given place. Light gets weaker and weaker as it gets farther and farther from its source. The increase in the area that the light must cover is proportional to the square of the distance that the light has traveled, as what is shown in the screen. For example, if we stand twice as far from the source, our eyes will intercept 2 squared or 4 times less light. If we stand 10 times farther from the source, then we get 10 squared or 100 times less light. Then you can see how this weakening means travel for sources of light at astronomical distances. One of the nearest star, which is Alpha Centauri A, emits about the same total energy as the Sun, but it is about 270,000 times farther away, and so it appears about 73 billion times farther. No wonder that the stars which close up would look more or less like the Sun look like pinpoints of light from far away. The idea that the apparent brightness of a source gets weaker with distance in the way we have described is known as the inverse square law. This inverse square law for light. The intensity of a 120 watts light bulb observed from a distance 2 meter away is 2.4 watts per meter squared. What would be the intensity if this distance was doubled? So the solution, if we move twice as far away, then the answer will change according to the inverse square of the distance. So the new intensity will be 1/2 squared is equals to 1/4 of the original intensity, or 0.6 watts per meter squared. So as was what shown in the solution, we get it by using the expression 1d squared, and if we plug 2 in the expression, then we have 1/2 squared is equals to 1/4, and then we come up with the result, which is 1/4 becomes the original intensity. And in order to get 0.6 watts meter per squared, then we divide 2.4 divided by 4, and then 2.4 divided by 4 is equals to 0.6 watts meter per second. Objects in the universe send out an enormous range of electromagnetic radiation. Scientists call this range the electromagnetic spectrum. Something that surrounds us, bombards us, some of which we can't see, touch, taste, or even smell. Every day, every space, everywhere we go. It is tasteless and odorless, yet we depend on it every second or every hour of every day. Without it, the world we know couldn't exist, and basically, it is electromagnetic radiation. The following are the types of electromagnetic radiation. Electromagnetic radiation with the shortest wavelengths, no longer than 0.01 nanometer, is categorized as gamma rays. The name gamma comes from the third letter of the Greek alphabet. Gamma rays were the third kind of radiation discovered coming from radioactive atoms when physicists first invented their behavior. And because gamma rays carries a lot of energy, this can be dangerous to our tissues or in our living tissues, or rather in us. Gamma radiation is generated deep into the interior of the stars, as well as by some of the most violent phenomena in the universe, such as the deaths of stars and the merging of stellar corpses. Gamma rays coming to Earth are absorbed by our atmosphere before they reach the ground. Thus, they can only be studied using instruments in space. Electromagnetic radiation with wavelengths between 0.01 nanometer and 20 nanometers is referred to as X-ray. Being more energetic than visible light, X-rays are able to penetrate soft tissues but not bones, and so allow us to make images of the shadow of the bones inside us. While X-rays can penetrate short length of human flesh, they are stopped by the large numbers of atoms in Earth's atmosphere which they interact. So X-rays is common to us. X-rays, as mentioned, is the radiation that has the capacity to see what's beneath the skin. Thus, X-ray astronomy could not develop until we invented ways of sending instruments above our atmosphere. Radiation intermediate between X-rays and visible light is ultraviolet, meaning higher energy than violet. Outside the world of science, ultraviolet light is sometimes called black light because our eyes cannot see it. Ultraviolet radiation is mostly blocked by ozone layer of Earth's atmosphere, but a small fraction of ultraviolet rays from our sun do penetrate to cause sunburn or extreme cases of overexposed skin cancer in human beings, which is really dangerous. Ultraviolet astronomy is also best done from space. Electromagnetic radiation with wavelengths between roughly 400 and 700 nanometer is called visible light because these are the waves that human vision can. Visible light obviously is the radiation that we can see by our naked eye. For example, light bulbs, sun. This is also the band of electromagnetic spectrum that most readily reaches Earth's surface. These two observations are not coincidental. Human eyes evolve to see the kinds of waves that arrive from the sun most effectively. Visible light penetrates Earth's atmosphere effectively except that when it is temporarily blocked by the clouds. Visible light and radio waves are the wavelengths of infrared or heat radiation. Astronomer William Herschel first discovered infrared in 1800 trying to measure the temperature of different colors of sunlight spread into a spectrum. He noticed that when he accidentally positioned his thermometer beyond the readest color, it still registered heating due to some invisible energy coming from the sun. This was the first hint about the existence of other bands of the electromagnetic spectrum, although it would take many decades for our full understanding to develop. A heat lamp radiates mostly infrared radiation, and the nerve endings in our skin are sensitive to this band of electromagnetic spectrum. So infrared are absorbed mostly by water and carbon dioxide, and this too is concentratedly low in our Earth's atmosphere. And for this reason, infrared astronomy is best studied in mountain tops, in high-flying airplanes, and in spacecrafts. So one of the example of infrared radiation is our common remote control that we use in controlling the TV. So the remote control acts as the transmitter to that picks up the command of the user and accordingly generates a binary signal, and then it travels through the air until it reaches the receiver, and the moment that the receiver reaches, and the moment that the infrared light, the encoded infrared light reach the receiver, then it will execute the command of the user. After the infrared, so here comes the familiar microwave. So microwave is familiar commonly to all of us. It is used in a short communication and microwave ovens. It has a wavelengths that vary from 1 millimeter to 1 meter and are absorbed by water vapor, which makes them effective in heating foods. So commonly the microwave oven. The micro prefix refers to the fact that the microwaves are small in comparison to radio waves, the next on the spectrum. So now, you might remember that the tea, which is full of water, heats up quickly when you put it in the microwave oven, while the ceramic cup, from which water has been removed by baking, stays cool in comparison. So we come now to the basic example of microwave, which is a microwave oven. So a microwave oven has a magneton present in its internal parts. And then the emitted radiation get reflected in the and then sa metallic surface of the oven, and then gina-absorb siya sang food particles. And then this property of microwaves is utilized, of course, to heat and cook food. All electromagnetic waves longer than the microwaves is called radio waves. So we all know that radio waves transfer information. And radio waves is a broad category that we divided it into subsection, which is the radar waves and AM waves. Radar waves, which are used in radar guns by traffic officers to determine vehicle speeds, and AM waves, which was the first to be developed for broadcasting. So Radio, for example, radio broadcasting is the prime application of radio waves. And then the wavelengths of these different categories range from over a meter to hundreds of meter, and other radiation can have wavelengths as long as several kilometers. So it could reach a wide range of distance. And then with such a wide range of wavelengths, not all radio waves interact with Earth's atmosphere in the same way. FM and TV waves are not absorbed and can travel easily through our atmosphere. AM waves are absorbed or reflected by a layer in Earth's atmosphere we called ionosphere. The ionosphere is a layer of charged particles at the top of our atmosphere produced by the interactions with sunlight and charged particles that are ejected from the sun. I hope that this brief survey has really given you a strong information. Although visible light is always associated with the astronomy, then we must understand, as what I say in the last discussion, that a visible light, or the light we see, is only a tiny fraction of a wide range of waves generated from the universe. Then today we understand that judging an astronomical phenomenon by only using what our eyes can see, or the visible light, is like going in a party and then hiding inside a table, only seeing their shoes and judging based on what you saw in their shoes without even seeing the whole being of a person. So it's like telling us na there is more than what our eyes can see, like naga-hide sa table, then there is more than that person than what we are seeing under the table, which is in relation to the astronomy. There is more to visible light to what our eyes could see. And then for us who study astronomy, it is important to avoid what we call a visible light chauvinist, which means to respect only what our eyes could see and not appreciating the result of instrumental experiments, or ignoring the information gathered by instruments sensitive to other bands of electromagnetic spectrum. Thus, it only means that, as what I've always stated, there is more than our eyes could see. A light is only a tiny fraction of a wide range of electromagnetic spectrum. So the table summarizes the bands of electromagnetic spectrum and indicates the temperature of typical astronomical objects that emits each kind of electromagnetic radiation. So the table shows the summarization of electromagnetic. Come now to the radiation and temperature. Some of astronomical objects emits mostly infrared radiation, other mostly light, and still others mostly ultra-red radiation. So, as what is discussed in the past topics, now you may understand that as you look around you, there are actually radiation swirling and moving inside your room or to wherever you are, rather than what you are just seeing, which is the visible light. What determines the type of electromagnetic radiation emitted by the sun, stars, and other dense astronomical objects is the so-called, and turned out to be, temperature. At the microscopic level, anything in nature is in motion. A solid is composed of molecules and atoms in continuous vibration. They move back and forth in place, but their motion is much too small for our eyes to make out. A gas consists of atoms or molecules that are flying about freely at high speed, continually bumping into one another and bombarding the surrounding matter. The hotter the solid or gas, the more rapid the motion of its molecules or atoms. The temperature of something is thus a measure of the average motion energy of the particles that make it up. This motion at the microscopic level is responsible for much of the electromagnetic radiation on Earth and in the universe. As atoms and molecules move around, about, and then collide, all vibrate in place. Their electrons give up electromagnetic radiation. The characteristics of this radiation are determined by the temperature of those atoms and molecules, so mostly it's their temperature. In hot material, for example, the individual particles vibrate in place or move rapidly from collisions. So the emitted waves are on average and more energetic. And recall that the higher waves have higher frequency. In a very cool material, the materials have low energy atomic and molecular motions, and thus it generates a lower energy waves. The radiation laws. To understand in more quantitative detail the relationship between temperature and electromagnetic radiation, we imagine an idealized object called a black body. Such an object, unlike your sweater or your astronomy instructor's head, does not reflect or scatter any radiation but absorbs all the electromagnetic energy that falls onto it. So, black body simply absorbs all the radiation. The energy that is absorbed causes the atoms and molecules to vibrate or move around in its increasing speeds. As it gets hotter, this object will radiate electromagnetic waves until absorption and radiation are in balance. We want to discuss such an ideal objects because you will see that the stars behave in very nearly the same way. The radiation from a black body has several characteristics which will be shown in the figure later. And then the word power means the energy coming off per second, and is typically measured in watts, which you are probably familiar with. For example, you are buying a light bulb, so we use the word watts. First of all, notice that the curves show that at each temperature our black body object emits radiation at all wavelengths. This is because in any solid or denser gas, some molecules or atoms vibrate or move between collisions slower than average, and some move faster than the average. So when we look at the electromagnetic waves emitted, we find a broad range or spectrum of energies and wavelengths. More energy is emitted and at the average vibration or motion rates. But if we have a large number of atoms or molecules, some energy will be detected at each wavelength. And then, second, note that an object at a higher temperature emits more power at all wavelengths than does a colder one. In a hot gas, for example, the atoms have more collisions and give off more energy. In the real world of the stars, this means that the hotter stars give off more energy at every wavelength than the colder ones. Third, the graph shows us that the higher the temperature, the shorter the wavelength at which the maximum power is emitted. Then we must all remember that a shorter wavelength means a higher frequency and energy. It makes sense then that hot objects gives off a larger fraction of their energy at shorter wavelengths than the cool objects. Then you may have observed, for example, this rule in our everyday life. For example, when a burner on an electric stove is turned on low, it emits only heat, which is infrared radiation, but does not go with its visible light. If the burner is set to a higher temperature, it starts to glow a dull red. At a still higher setting, it goes a brighter orange red, and then which is a shorter wavelength. At even higher temperature, which cannot be reached with ordinary tubes, metal can appear brilliant yellow or even blue-white. We can use these ideas to come up with a rough sort of thermometer for using the temperatures of the stars. Because many stars give off most of their energy in visible light, the color of the light that dominates a star's appearance is a rough indicator of its temperature. Then, I must give you some examples. Like, if one star looks red and another looks blue, which one has the higher temperature? And if your answer is blue, then you are correct. Because blue is the shorter wavelength color, it is the sign of the hottest star. And then note that the temperatures we associate with different colors and signs are not the same as the one artist is using. In art, red is often called hot color and blue is the cool color. Likewise, we commonly see red in the faucet or air conditioning colors to indicate hot temperature and blue to indicate cold temperatures. Although these are the common uses to us in daily life, it's in another way around. The wavelength at which maximum power is emitted can be calculated according to the equation. Where the wavelength is in nanometer, 1 billion of a meter, and the temperature is in K, the constant 3 times 10 raised to 6 has units of nanometer times K. The relationship is called the Ionosphere law. And for the sun, the wavelength at which the maximum energy is emitted is 520 nanometers, which is near the middle of that portion of the electromagnetic spectrum called the visible light. So this is the example 5.3. So calculating the temperature of a black body. We can use Finn's law to calculate the temperature of a star provided we know that the wavelength of peak is the intensity for its spectrum. If the emitted radiation from a red dwarf star has a wavelength of maximum power at 1200 nanometer, what is the temperature of the stars, assuming it is a black body? So we use the formula and substitute the given information and come up with the results of 2500 K. So we can also describe our observation that hotter objects radiate more power at all wavelengths in a mathematical form. If we sum up the contribution forms all parts of the electromagnetic spectrum, we obtain the total energy emitted by a black body. What we usually measure from a large object like a star is the energy flux, the power emitted per square meter. The word flux means flow. Here we are interested in the flow of power into an area. It turns out that the energy flux from a black body at temperature T is proportional to the fourth power of its absolute temperature. The relationship is known as the Stefan Boltzmann Law and can be written in the form of an equation as where F stands for the energy flux and Greek letter sigma is a constant number 5.67 times 10 raised to negative 8. Now, notice how impressive this result is. Increasing the temperature of a star would have a tremendous effect on the power it radiates. For example, the sun were as twice hot, that is, it had a temperature of 11,600 K. It would radiate 2 raised to 4 or 16 times more power than it does now. Tripling the temperature would raise the power output 81 times. Hot stars really shine away a tremendous amount of energy. Now we should look at the example in the screen. So calculating energy flux tells us how much power a star emits per square meter. We would often like to know how much total power is emitted by the star. We can determine that by multiplying the energy flux by the number of square meters on the surface of the star. Stars are mostly spherical, so we can use the formula 4 pi r squared for the surface area, where r is the radius of the star. The total power emitted by the star can be found by multiplying the formula to energy flux at the formula for the surface area. So we come up with that formula. And then the examples would be two stars of the same size and are the same distance from us. Star A has a surface temperature of 6,000 K, and star B has a surface temperature twice as high, which is 12,000 K. How much more luminous is star B compared to star A? So basically, the solution is shown on the screen, substituting the given informations and come up with the results of 6. So we come now to spectroscopy and astronomy. As what is mentioned in the past discussion, we all know that electromagnetic radiation carries a lot of information about the nature of the stars and other astronomical objects. And to extract this information, however, astronomers must be able to study the amounts of energy we receive at different wavelengths of light in fine detail. So let's examine how we can do this and what we can learn. First, we have the properties of light. Light exhibits a certain behaviors that are important to the design of telescopes and other instruments. For example, light can be reflected from a surface. If the surface is smooth and shiny as like the mirror, then the direction of the reflected light beam can be calculated accurately from the knowledge of the shape of the reflecting surface. Also, light is bent or refracted when it passes from one kind of transparent material into another, say from the air into a glass lens. So the properties of light had been all common to us, because this has been the past lessons in our physics. So reflection and refraction of light are the basic properties that make possible all optical instruments, from eyeglasses to giant astronomical telescopes. Such instruments are generally combinations of glass lenses, which bend light according to the principles of refraction, and curved mirrors, which depends on the properties of reflections. So small optical devices such as eyeglasses and binoculars generally use lenses, whereas large telescopes depend almost entirely on mirrors of their main optical elements. So we will discuss astronomical instruments and their uses more fully in astronomical instrumentations. For now, we turn to another behavior of light, one that is essential for the decoding of light. In 1672, the first paper that he submitted at the Royal Society, Sir Isaac Newton described an experiment in which he permitted sunlight to pass through a small hole and then through a prism. And then Newton found that the sunlight, which looks white to us, is actually made up of mixture of all the colors of the rainbow. So as what is shown in the screen, it shows how light is separated into different colors with prism, a piece of glass in shape of a triangle with a refracting surface. Upon entering one face of the prism, the path of the light is reflected or bent, but not all the colors are bent but by the same amount. So the bending of the beam depends on the wavelength of the light as well as the properties of the material, and as a result, different wavelengths are bent by different amounts and therefore follow slightly different paths through the prism, like how the violet light is bent more than red. This phenomenon is called dispersion and explains Newton rainbow's experiment. And then upon leaving the opposite face of the prism, the light is bent again and farther dispersed. If the light leaving the prism is focused on a screen, the different wavelengths of colors that make up the light are lined up side by side, just like a rainbow. So is what you can see in this figure. In fact, a rainbow is formed by the dispersion of light through raindrops, because this area of colors is a spectrum of light, and then the instrument used to disperse the light and form the spectrum is called a spectrometer. So we come now to the value of stellar spectra. When Newton described the laws of refraction and dispersion in optics and observed in the solar spectrum, all that he could see was a continuous band of colors. If the spectrum of the white light from the sun and stars were simply a continuous rainbow of colors, astronomers would have little interest in the detailed study of the star's spectrum once that they had learned it is average surface temperature. And in 1802, however, William Wollaston built an improved spectrometer that included a lens to focus the sun's spectrum on the screen. With this device, Wollaston saw that the colors were not spread out uniformly, but instead, some ranges of colors were missing, appearing as dark bands in the solar spectrum. And then he mistakenly attributed these lines to natural boundaries between the colors, and in 1815, German physicist Joseph Fraunhofer, upon a more careful examination of the solar spectrum, found about 600 such dark lines, or the missing colors, which leads scientists to rule out the boundary of hypothesis. Then, later, researchers found that similar dark lines could be produced in the spectra, and spectra is the plural of spectrum. And then it's artificial light sources. They did this by passing their light through various apparent transparent substances, usually containers with just a bit of thin glass in them. These gases turned out not to be transparent at all colors. They were quite opaque, and a few sharply defined wavelengths, something in each gas, had to be absorbing just a few colors of light and no others. All gases did this, but each different element absorbed a different set of colors and thus showed different dark lines. If the gas in the container consisted of two elements, then light passing through it was missing the color for both of the elements, so it became clear that the certain lines in the spectrum go with certain elements. This discovery was one of the most important steps forward in the history of astronomy. And then, what would happen if there were no continuous spectrum per hour gases to remove light from? What if instead we heated the same gases until they were hot enough to glow with their own light? When the gases were heated, a spectrometer revealed no continuous spectrum, but several separate bright lines. That is, these hot gases emitted light only at certain specific wavelengths or color. So, in this figure, when the gas was pure hydrogen, it would emit one pattern of colors. When it was pure sodium, it would emit a different pattern. A mixture of hydrogen and sodium emitted both sets of spectral lines. The color the gases emitted when they were heated were the very same colors as those they have absorbed when a continuous source of light was behind them. And then, for such experiments, scientists began to see the different substances showed distinctive spectral signatures by which their presence could be detected. So, just like your signatures that allows the bank to identify you, the unique pattern of colors for each type of atom can help us identify which element or elements are in gas. So we come now to the types of spectra. In these experiments, then there were three different types of spectra: a continuous spectrum, absorption spectrum, and emission spectrum. A continuous spectrum form when a solid or very dense gas gives off radiation in an array of all wavelengths or colors of the rainbow. A continuous spectrum can serve as a backdrop from which the atoms of much less dense gas can absorb light, and then a dark line or absorption spectrum consists of a series or pattern of dark lines missing colors superimposed upon the continuous spectrum of a source, and then a bright line or emission spectrum appears as a pattern or series of bright lines. It is consists of a light in which only certain discrete wavelengths are present. Then, when we have a hot-end glass, each particular chemical elements or compound produces its own characteristics pattern of spectral lines. It is spectral signature. No two types of atoms or molecules give the same patterns. In other words, each particular gas can absorb or emit only certain wavelengths of the light peculiar to that gas. In contrast, absorption spectra occur when passing white light through a cool, thin glass. The temperature and other conditions determine whether the lines are bright or if it's dark, but the wavelength of the lines for many elements are the same in either case. It is the precise pattern of wavelengths that makes a signature of each element unique. Liquids and solid can also generate spectral lines or bands, but they are broader and less defined. They are less defined, and hence more difficult to interpret. Spectral analysis, however, can be quite useful. It can, for example, be applied to light reflected off the surface of a nearby asteroid as well as to light from a distant galaxy. The dark lines in the solar spectrum thus give evidence of certain chemical elements between us and the sun, absorbing those wavelengths of sunlight. Because the space between us and the sun is pretty empty, astronomers realize that the atoms doing the absorbing must be in a thin atmosphere of color gas around the sun. This outer atmosphere is not all that different from the rest of the sun, but just thinner and colder. Thus, we can use what we learn about its composition as an indicator of what the whole sun is made of. And then, similarly, we can use the presence of absorption and emission lines to analyze the composition of other stars and clouds of gas and space. Such analysis of spectra is the key to modern astronomy. Only in this way we can sample the stars which are too far away for us to visit. And then encoded in the electromagnetic radiation from celestial objects is clear information about the chemical makeup of these objects. Only by understanding what the stars were made of could astronomers begin to form theories about what made them shine and how they evolved. In 1860, German physicist Gustav Kirchhoff became the first person to use spectroscopy to identify an element in the sun, and then he found that the spectral signature of the sodium gas. And then in the years that follow, astronomers have found many other chemical elements in the sun and stars. In fact, the element helium was found first in the sun from its spectrum, and only later identified on Earth. And then the helium comes from Helios, the Greek name for the sun. So the rainbows is an excellent example of dispersion of light, or sunlight rather. We all have a good chance of seeing a rainbow anytime in between the sun and in rain shower, as illustrated in the figure. The raindrops act like prisms and break white light into the spectrum of colors. Suppose a ray of sunlight encounters a raindrop and passes into it. The light changes direction, is refracted. When it passes from air to water, the blue and violet light are refracted more than the red. Some of the light is then reflected at the backside of the drop and re-emerge from the front, whereas it again refracted. As a result, white light is spread out into a rainbow of colors. And then note that the violet light lies just above the red light after it emerges from the raindrop. And then when you look at the rainbow, however, the red light is higher in the sky. The question is why? And then look again in the figure. If the observer looks at the raindrop that is high in the sky, the violet light passes over her head and the red light enters her eye. Similarly, if the observer looks at the raindrop that is low in the sky, the violet light reaches her eye and the drop appears violet, whereas the red light from the same drop strikes the ground and is not seen. Colors of intermediate wavelengths are refracted to the eye by the drops that are intermediate in altitude between the drops that appear violet and ones that appear red. Thus, a single rainbow always has red on the outside and violet on the inside.